Okay, this is lecture over Module 4 of your curriculum entitled The Physical Layer. If we go through and look at this, the first section is always, why should I take this module? Basically what we're going to learn about in Module 4 is the bottom layer of the TCP IP stack, which is referred to as the physical layer. Some of the things we're going to learn about are listed here in 402. We're going to learn about the physical layer. Why do we have it? We're going to talk about some of the characteristics of the physical layer, and then we're going to talk about cabling or media, in particular copper cable, in particular for that unshielded twisted pair cable, which is copper. We'll talk about fiber optic cabling, and we'll talk about wireless media or communicating in a wireless network. So, what is the purpose of the physical layer? First of all, and most importantly, it's what actually creates the network that we're going to use to communicate between devices. One thing they're showing us here is they're showing us a wireless router. So it is a router, it is a switch, it is a wireless access point, it is a number of things, but we're looking at the back of it, and of course we have power, we have a power light, we have what appears to be an activity light, and then we have a physical connection that it comes from the internet. So if we have a cable modem or a DSL modem or something like that, the connection will come from the modem and connect in to this wireless router. And one thing that we might do is, I said this was a switch also, we talked about switches in the past. So you have 4 connections for Ethernet. And what they're showing you here is we're actually using an Ethernet cable, and we're plugging it into one of the ports on our wireless router. And then what we're doing is plugging the other end into what they're calling an Ethernet NIC. So a NIC is a network interface card, and we have one of those here, and we can plug our connection in to provide a wired connection to this laptop. The bottom layer, and also they mentioned TCP/IP in the intro, and now they're mentioning OSI. The bottom layer in both of those models is the physical layer. So basically what they're talking about here in 4.1.2 is a number of things. First, the physical layer provides a way to transmit bits, and that is the layer 1 PDU, Protocol Data Unit. We talked about that in Module 3, I believe. And those bits come from a frame, which is the layer 2 PDU. So we've seen this graphic a number of times. Basically what we're doing is we are encapsulating data and putting that in, breaking that into TCP segments. We then pack those TCP segments into an IP packet, which in turn gets stuffed into an Ethernet frame. That frame is then turned into bits and is transmitted over our network. So again, to sum this up, the physical layer is the way that we get the ones and zeros that represent our information to travel across the network. 413 is a check your understanding on the physical layer. You can do that on your own. And we'll move on to physical layer characteristics. There are a number of standards that we have with all kinds of computer and networking equipment and networking in general. So if you look at this table, just at the physical layer, here's 6 organizations, six standard organizations that create standards that have to do with the cabling, the NIC cards, how we transmit data, which is referred to as the signaling. Then if we go down here and look at the OSI model, again, this is the 7 layers of the OSI model we discussed in Module 3. You'll see that the Internet Engineering Task Force is responsible for most of TCP IP, but when we get down to the physical and about half of the data link layer, there are 5 other organizations that do things just because that's at the physical layer. There's lots of things going on there. If we talk about the actual physical components that we have the physical components, which are the wires, the connectors, that type of thing. But we have to also have a way to encode our information into ones and zeros, and then we have to put those ones and zeros on the physical layer, which is referred to as a signaling. So we're going to talk about encoding and signaling a little more. So basically, as they say here, encoding is a method of converting a stream of data bits into a predefined code. So we have ones and zeros that make up the information that we want to send. And here is one of the first encodings that was used for sending digital data, that is ones and zeros, over the internet. So I don't know if they mentioned that or not, but these little lines that make up the columns here are called a bit time. A bit time is the length of time that is required to transmit a single bit. So within those bit times, we have transitions either from a high voltage to a low voltage or a low voltage to a high voltage. And what they're trying to show us here is in the middle of the bit times, here we have a transition from a high voltage to a low voltage. That's how we represent a 0. We represent a 1 by going from a low to a high value. Notice here that, again, we turn around and go from a high to a low, but we need to go from high to low again, so this signal has to go all the way back up to a high so that we have a high to low transition during this bit time. So that's referred to as Manchester encoding, and like I said, that's one of the simplest encodings and one of the first encodings. Signaling is putting the electrical signal, in the case of copper, on the wire, or pulses of light for fiber optic cable. So this is what the voltage is actually going to look like. It's much more complicated than the Manchester encoding, but these transitions are representing the ones and zeros in our data. And in the case of copper cable, we are using voltage. If we click on fiber optic cable here, we're going to use light pulses. Fiber optic cable, which we'll talk about a little bit more later, is either glass or plastic. It's very finely, very precision drawn plastic or glass. If we're using plastic, these pulses of lights are typically created by an LED, a light emitting diode. If we are using glass fiber optic cable, then often those pulses of light are created by an actual laser. And then if we talk about wireless, we have radio waves, and we have a digital signal that we want to send that's ones and zeros, and we have different ways we can do that. And a couple of these sound like what you might have on your radio. So we have AM, which is amplitude modulation. So by modulating the amplitude of the wave, we can represent the ones and zeros in our message. We also might have frequency modulation, where zeros are a lower frequency and the ones are higher frequencies. And then we may have phase modulation. So here you see we have a sine wave that kind of starts out at 0, goes to a max, to a min. But here all of a sudden, instead of continuing up, it goes down. So it's basically phase shifting by 180 degrees. So, we may use amplitude modulation, frequency modulation, or phase modulation to represent the data in the case of a wireless network. One term or concept that we need to be familiar with is bandwidth, and there's several things related to that. Basically, bandwidth is how much data you can move across the network, and these days it's typically measured in megabits per second. So the first thing to point out in this table is that everywhere we have a lowercase b. Lowercase b means bits. If we have GB, where B is a capital B, then we would be talking about gigabytes. So it's important to look at that. The amount of data, or the bandwidth that we can move over a cable, depends on a number of things. First of all, it depends upon what the physical media actually is. And then it also depends on how we are signaling and detecting that signaling on the network. Both those things can factor into the bandwidth. Some related terminology is listed here. Latency is basically delay. From the time you send a bit till the time it is delivered is its latency. High latency is bad if it takes a long time to transmit the data. We expect things to happen almost instantaneously these days in electronics and computers, so we are shooting for low latency. Throughput is a measure of how much data is actually traveling over the network in a period of time. If we are talking about 100 megabit connection, then in theory 100 million bits is what we could send in a given amount of time. The reality is we don't actually get that. We get a little bit lower. So what we actually get is throughput. There's also another term. I'm not a big fan of this term, but it's in the curriculum, so we'll talk about it, which is goodput. There's a lot of overhead when we do encapsulation. We talked about adding headers and possibly trailers to data as we encapsulate it. That all takes up space that is not actually data that we're transmitting. So goodput is the measure of actual good usable data that is being transmitted minus any overhead. Down here at the bottom, they're showing a speed test. You had a homework where you had to do one of these. Basically, this is measuring at that point in time how much data down are you receiving and how much up are you receiving. So, this is probably a 100 megabit per second connection, and you're getting 80 megabits down, and you're getting about 9 megabits up. That's a pretty decent connection. 472 is a check your understanding over the physical layer. You can do that on your own, and we'll move into talking about copper cabling. Copper cabling, as the name implies, is made out of copper. Copper is a good conductor of electricity, and we're going to use electrical signals over the copper cable to represent our ones and our zeros that we are transmitting. A couple of things they're talking about down here is electromagnetic interference or radio frequency interference. That is the fact that if we have copper cable and it's in the vicinity of electromagnetic field, that there may be signals induced upon that cable. And the crosstalk is the fact that if we transmit data on one cable and there's another cable close by, we may have that electromagnetic interference, which introduces stray electrical signals on that wire, which is not desirable. So you want to reduce crosstalk. So to kind of show you the problem, here we have a pure digital signal. This is what we hope we are transmitting to represent the strings of ones and zeros. If we are having interference introduced on the cable transmitting this signal, these are going to add together. And this is what the voltage is going to look like with the interference. And, you know, it doesn't do a whole lot, but right here, it changed that 0 to a 1. So we get an incorrect message or strings of bits being sent to the device because of the interference that the cable is receiving. So that's one of the drawbacks to copper cable, is it's susceptible to electromagnetic interference. Now, a couple of the advantages are it's a good conductor of electricity, and it's relatively cheap to purchase and install, and it's pretty durable and not likely to break. So in networking, we have different types of copper cabling. The most common is shown in the top left. That's unshielded twisted pair, which is usually represented as UTP. We'll talk about each of these in more detail in the sections following. To the right, we have shielded twisted pair cable, where we have twisted pair with something that's kind of similar to aluminum foil wrapped around it. And I really want to point this out because when they show us shielded twisted pair a little later down, it's going to be slightly different, and I'll point that out. And then we might have coaxial cable. As the name implies, coaxial means you have things that share a common axis. The axis would be down the middle of this wire. So we have this conductor, and then we have this shielding all the way around. So the signal goes down the conductor in the middle and returns over the shield. So delving a little deeper into this, unshielded twisted pair, the name comes from the fact that we have 4 pairs of wires that are twisted around each other. This is to attempt to cancel out some of the electromagnetic interference. It is unshielded, so we do not see the shield, but we do have an outer jacket here which is going to protect and present this as a single cable instead of these twisted pairs. Also, these twisted pairs have plastic coatings on them, primarily to keep them from shorting out with each other, but also to represent colors of the pairs, so that when we go to put these in a jack, we know how to do that. Shielded twisted pair, there's kind of 2 flavors. We saw the one before where you had the 4 twisted pairs and there was a single conductor or foil around it. Here, each of the individual pairs have a foil around it, and then all 4 pairs have another foil or shielding around it. So it's kind of doubly shielded. And then also we have the outer jacket, again, to protect all this and to present it as one cable. In the case of coaxial cable, we kind of have it stripped back here. We have the conductor in the middle, we have an insulator, we have the shield, and we have the outer jacket. So here's kind of a sliced away view. Here's one on the bottom. Not really sure why the connectors are not imaging. A BNC connector is one that you push on and kind of twist and it snaps into place. An F connector is what, if you have cable TV or satellite satellite system, like Dish or DirecTV, that's typically going to be an F-type connector. So, 436 is checking your understanding on copper cabling. So as always, you can do that on your own. And we will move on to unshielded twisted pair, UDP. So I mentioned this before. A couple of things we need to talk about when we're talking about twisted pairs: cancellation. By twisting the pairs, we have a cancellation of electromagnetic interference, trying to take that to zero, or at least a very low amount. And then another thing in the standards, and we'll see more about the standards later down, is the higher the standard, like as we move from Cat 3 to Cat 5 to 5e to 6, there has to be more twist per inch. And the reason for that is you work at higher frequencies, which is how you move data faster. So as new technologies come out and move data faster over copper wiring, that increases the possibility of crosstalk. And by putting more twist per inch, that helps reduce the crosstalk. So that's why we have mentioned the twist per wires. There are standards related to cabling. They talk about what type of cable you have. They talk about what is the possible length. For example, Ethernet cable, 100 meters is the maximum you should have for that. It specifies what type of connectors, what are their size, how are they terminated, which is the next thing. And then it also has a lot of test criteria, what frequency it has to work at, what's the maximum amount of crosstalk that is allowed, etc. So IEEE does a lot of these standards, the Institute of Electrical and Electronics Engineers. I mentioned categories of cable. I just said Cat 3, but it's shortening of Category 3. So Cat 3 was originally for telephones, and they started transmitting data over those. As the speed increased, we came out with Cat 5 and later Cat 5e for a 100 megabit connection, and with 5e, gigabit or 1000 megabit per second transmission. Cat 6 has extra separation between each of the cables. We can see down here in the figure. Each of them are separately shielded. You can go up to 10 gigabits per second. You have Cat 7 cable and Cat 8 cable supporting 10 and 40 gigabits per second. So that's what the categories are. Now, I said putting it in the jack earlier. I really meant putting it into the plug. So there are standards about this RJ45 jack, plug, and then socket or jack down here. RJ stands for registered jacks. The two most common you hear about is RJ45, which is for Ethernet, and RJ11, which is for telephones. Years ago when telephones came out, they're like, we need a jack. It needs to have 4 connectors. Here's what size it is. Okay, you're assigned registered jack 11. Time went by by the time they got around to specifying Ethernet cables, the next available number was 45. So registered jack 45 or RJ45. So the wires come up into the plug, and there are 8 connectors here that make contact with the 8 wires. This is a jack. It has a punch down in the back for wires. This is the jack you would see in the wall. You would then plug your Ethernet cable into that to make a network connection. Up here we have a nicely terminated plug where the shielding goes in and is clamped down upon as a stress relief, and the wires go up and make proper connection into the plug. Down here we have a poorly terminated one. First of all, we have wires outside, and the person looks like they didn't even push the wires all the way up. so that the pins would make connections with them. Sometimes you see some that are in an angle where some have good connections, and then you might work your way over here where you have one or two wires that do not have connections. Obviously, if you don't have all 8 connections, all 8 nice connections, good connections, your cable is not going to function correctly. So here we're showing a properly terminated cable. You push the wires in the correct order, which we'll talk about here in a moment. The crimper pushes these metal pins down into the wires. Also, there's a little kind of triangle that gets pushed into the outer casing of the wire. And again, that's so if you yank on this wire, you're yanking here on this connection, not yanking here on the electrical connection, and risking damage to the cable. When we talk about cables in networking, we talk about straight through cables, and we talk about crossover cables. So if we're connecting like equipment, that is like computer to computer, switch to switch, we need to use something called a crossover cable that crosses over transmit to receive. A straight through cable, pin 1 goes to 1, 2 goes to 2, 3 goes to 3, all the way to 8 goes to 8. So the connectors run straight through, if you will. There are 2 standards for this. They both start with T568, but there's an A connector and a B connector. And this is showing the 8 pins, the 4 pairs, and how they need to be connected. So the green pair would be a solid green, and then one called green white that either had a green stripe on white or, as shown here, less likely a white stripe on a mostly solid green wire. So this is the order you have to put the 8 wires in to have an A connector. To have a B connector, it's slightly different. So, 1, 2 goes to 3, 6, coming back 1, 2 goes to 3, 6. That's transmit and receive. So to make a straight through cable, you wire a cable that either has an A connection on both ends or a B connection on both ends. And all the pins would go, quote, straight through. If you need a crossover cable, you wire an A on one end and a B on the other end. And then, like I said, that will cross transmit and receive, or pins 1 and 2 will cross over to pins 3 and 6. Okay, so straight through cable, crossover cable. We also have something that's considered a Cisco proprietary cable, which is a rollover cable. And in a rollover cable, pin 1 goes to pin 8 on the other side, 2 goes to 7, 3 goes to 6, etc. The way you make a rollover cable is you wire an A or a B jack on one end, and then you take the same plug at the other end, but you flip it upside down before you crimp it. And that makes a rollover cable. And the purpose of a rollover cable is to connect the serial port on a laptop to either the console or auxiliary port on a switch or a router or other Cisco equipment. One thing that used to be a really big deal and things students worried about is actually going through and making sure that you could make cables. Obviously, with this being an online class, we're not going to make cables. But here's an activity to make sure you can do a pinout or a T568B pinout. And basically what you do is you click the color and then you click the wire in there. You can go through and do that. You can check it. You can say, show me the correct colors. And then you can reset it back and try again. So slightly different activity than we've seen before. Moving on to fiber optic cable. There are several things. Again, fiber optic cable is precision drawn plastic or glass. It's typically high speed. It can go for much longer distances than, and also operate at a higher bandwidth than copper cable, the one we've talked about the most. They're telling you can kind of imagine this as a empty paper towel roll with a mirror on the inside, and then we're sending pulses of light through that tube. There are different types of fiber. I used to tell my students that everything you would think about fiber is backwards. For example, I'd ask students, do you think single mode fiber or multi-mode fiber is better? And they'd say, oh, multi-mode, because it has the word multi. Actually, in reality, single mode fiber is better. In the case of single mode fiber, we have a very small glass core. We have a cladding, which has kind of that mirror effect and also protects the fiber. And then we have the coating on the outside to protect the cable. Fiber optic cable is fragile compared to copper cable, so that's one of the disadvantages. Another disadvantage is it's much more expensive than copper cable. If we look at multi-mode fiber, the core is much bigger, which kind of allows the light to bounce around. And that can cause issues with the signaling. So we can't run for as long as distance, for example. Where do we use fiber optic cable? We use it in enterprise networks. At the KCTCS office in Versailles or at the University of Kentucky data centers, and from router to router across campus. Often that is done with fiber. You can also have fiber to the home. Verizon, I believe, was one of the first people to do that in Lexington. We now have MetroNet, who is doing that, giving high-speed connectivity to your house. Since they can go long distances, we have what we call long-haul networks. And then also submarine. And this does not mean like submarine as in the ship. It means sub, below, marine, water. So this is actually just cables running across the ocean to carry, telephone, computer, and other types of messages. As far as connectors, there's different types of connectors. This is called a straight through connector because basically the fiber, goes straight through and connects in and twist on, kind of like a BNC connector. We also have something called a subscriber connector, which is kind of similar, except we have a square snap-in type connector on the end. We have LC simplex connectors, very similar. They have this clip on there to clip it into place and to eject it. And then we have what's called duplex LC, which is where we have two of the LC connectors together. And the nice thing about this is, if you get them in the right connector, when you plug them in, they're going to be connected correctly for transmit and receive, which is why we have two fiber optic cables. We also have fiber patch cords. Patch cords are usually short or relatively short cables that are used for routing fiber around in a wiring closet or a data center. Here we have a straight SC to SC connectors on both ends. Here we have LC on both ends, but we can go straight through to LC or SC to straight through. So, depending upon what patch panel or what device or what piece of equipment we're plugging in, we may need different types of connectors on the end of the cable, or like in the case here, now they're both SC connectors. This table is a comparison. We've kind of been talking about this throughout, but a comparison of fiber and copper. Fiber is a much higher bandwidth. Uh, this can go 100 meters, whereas this can go up to 100,000 meters. Immunity to electromagnetic interference. It's really bad in copper cable. It's almost completely immune in fiber optics. Electrical hazards, same thing. There's low immunity to electrical hazards because copper conducts electricity. It is high in the case of fiber optic because plastic and glass do not conduct electricity. Again, installation and media is the lowest cost for unshielded twisted pair. It is the highest cost with fiber optic cable. And then as far as safety precautions, that is making sure you don't damage the cabling. You really have to worry about that with fiber optic cable. It is very fragile. So 457 is check your understanding over fiber optic cable. You can do that on your own. And we will move on to wireless media. So, these days we're familiar with tablets, laptops, smartphones using wireless media, but there are some limitations. The nice thing about wireless is it covers a big area. That can also be a disadvantage. It's pretty easy to install. It's relatively inexpensive to install, but you have to think about the limitation as far as the coverage. That is, it's a relatively small area, and if you have metal walls or even drywall walls, it's going to cut down on the signal as the wireless signal passes through that. Also, you can get interference from microwaves, 2 gigahertz cordless phones, a lot of things. Fluorescent lights even can cause interference and reduce the usability or the function of a wireless network. It's not the most secure, partially because the signal is transmitted in an area. Somebody could be sitting outside your house in your driveway trying to sniff or break into your network because the signal travels outside the house. Also, the encryption methods that are used in wireless are not as strong as some of the other encryptions that are used. And the fact that we have a share medium, we have to operate in something called half duplex as opposed to full duplex. And basically what that means for the point of this discussion is the bandwidth is cut in half. As far as wireless medium, there are several different types. Wi-Fi, which is IEEE 802.11. Ethernet is IEEE 802.3. We'll talk about that probably some point in the future. This is what we have in our house, and if you go to Chick-fil-A and they have Wi-Fi, this is what they're most likely going to have. Bluetooth, 802.15. This would be from your phone to your headset, from your phone to your car. Sometimes we have Bluetooth printers. A lot of times you wouldn't think about this, but it is a wireless network. It's just a different set of standards than Wi-Fi. Then we have WiMAX, which they say is a one-to-many broadband. So you might have a WiMAX ISP where they transmit a wireless signal over a wide area, part of a town, for example, and give Wi-Fi that way. And then there's something called Zigbee that is very low powered. It's used for industrial use, that is for things to communicate, for example, inside a factory. Or one thing that's become a very hot topic is the Internet of Things, where you're connecting all kinds of things to the Internet, basically. Doorbells, thermostats, refrigerators, etc. And Zigbee is sometimes used for Internet of Things devices. To create a wireless local area network, there's a couple things you need. Over here on the right, we have a wireless access point. These are antennas to receive and transmit data. So basically what happens is you would connect this to an Ethernet or some type of ISP, and then it will talk to your wireless devices. So as the name implies, this is how we access the wireless network. Now on our device, whether it be our tablet or laptop or phone, we're going to have a wireless NIC. So we talked about network interface cards in computers. Anything that talks to the network needs a NIC. So if we're doing a wireless network, we need a wireless NIC. 464 is a check your understanding. You can do that on your own. 465 is a packet tracer activity about connecting to a wired and wireless LAN. I am going to assign this packet tracer activity, so watch for it to appear in Blackboard in the near future. 466 is a lab about viewing wireless and wired NIC information. I may or may not assign that, so I'm leaning towards the fact that I will, so watch for that to appear in Blackboard as well. 471 is another packet tracer related to the physical layer. I will assign this packet tracer, so watch for it to appear in Blackboard. And then that brings us to the summary. What did I learn in this module? So you can go through and read this. It's just recapping everything we talked about in Module 4. That's followed by the module quiz for the whole module on the physical layer. As always, you can do that on your own. And that finishes up this module. Like I mentioned a couple times previously, in version 7 of the curriculum, the version we're using, we have module group exams. So your first module group exam was over chapters 1, 2, and 3. I went ahead and looked. The next group exam is over 4, 5, 6, and 7. So it'll be over this and 3 other modules as well. So that finishes up Module 4. I will continue on in Module 5 down the road.